Okay, I'll motivate it with the same example. So intuitive example. We wrote down those two equations. I'll write the same equations. Okay, we solve for x1. And for x2 using the second equation. Okay, now this is how you will start. You'll assume some value for x1, x2. That would be your first guess. So that 0 as a superscript indicates that's your iteration 0. Now we'll compute the value for x1 iteration 1. We use b1 minus a1 to x to 0 divided by a11. So this comes straight from this equation. Okay, now in the Jacobi iterative method, what we did was we took the second equation and we did this. That's the second equation. We did this. So what Gauss-Seidel does is it says that you already have an estimate for x11. Why use the old estimate? So it just replace this with x11. So that's the only difference. This goes in here. So that ends iteration 1. So from iteration 1, we got x11, x21. For iteration 2, we do the same thing. We first solve for x12 as b1 minus a12 x21 divided by a11. And x22 is b2 minus a21 x1, but from iteration 2, this is this one, x1 from iteration 2. It's a very minor modification. It's just changing one single thing. In this case, if it's of 3 dimensions, that is x1, x2, x3, then you will just keep updating the values of x's based on what you compute in the very same iteration. Okay, so what I'll do is I'll take the same problem, we'll solve it, and we'll see if there's an improvement in the solution, the final value, and improvement in the number of iterations. Yeah, and you can use the same termination criterion as one before. Okay, so here's the problem. I would call it example. Following system of equations. Okay, they are 2x1 plus x2 plus x3 equals 7, x1 minus 3x2 plus x3 equals minus 2, 2x1 plus 2x2 minus x3 equals 3. Okay, so the problem is solve using Gauss-Seidel method. Show calculations for just 3 iterations. It takes more than 3 iterations to solve this one. And use an initial guess of 0, 0, 0. Okay, the first step for a problem like this is to solve for x1, x2, and x3, like write an equation, so that we can do the iterative process. So let's write that. So first we'll write an equation for x1. So it'll be x1 equals 7 minus x2 minus x3 divided by 2. x2 equals 2 plus x1 plus x3 divided by 3. x3 equals 3 plus minus 3 plus 2x1 plus 2x2. Okay, so we know that we've been given the initial guess. It's 0, 0, 0. So let's start. Yeah, question. No, you can guess whatever you want.
Well, I mean, like, is there ever like a benefit to like
if you
tell me, like, oh, maybe I should guess this?
Yeah, so if you have a hunch that the solution is close to 1 to the solution is 1 to 3. So if you have a hunch that the solution is near 1 to 3, you're much better off choosing maybe close to 1 to 3. I'll show you the numerical code, the octave code today, and we can just try and number of guesses and see what the output is. But yeah, there is nothing stops you. The reason why I give you initial guess is because in the exam, it's much easier to give you initial guess so everybody gets the same answer. That's the only reason. But yeah, you should just use whatever is you think is the close to the solution. Okay, so x11, use the first equation, 7 minus 0 minus 0 divided by 2, which is 3.5. Okay, now the thing with this is that now you need to update the value in order to proceed. So what I do is, just to make my life easy, I just write it down here. My new x1 is 3.5. My x2 is 0. It's not changed. And x3 is 0. Okay, so now I'll use these values to populate my next guess for x21. So it's 2 plus x1. So don't use this x1. You need to use the new x1. So that'll be 3.5. X3, which is 0, divided by 3. Okay, that comes out to be 1.8333. So now update the value. So keep x1 as it is, 3.5. X2 is 1.833. X3 is still 0. So now we'll update x3, 1. So go by the formula, minus 3 plus twice x1, but x1 is 3.5. Plus 2 times x2. This is the new x2, 1.8333. Okay, that comes out to be 7.6667. Okay, so that was just iteration 1. It's not too bad, right? So just a little bit of crunching numbers. Okay, now what I'll do is, there's a very specific reason I wrote the solution, because I'm just going to carry that forward. It's always good to have it on the side when you're doing the calculation. Copy. Okay, let's paste it somewhere here. So we are at iteration number 2. Our solution from the first iteration is x11 is 3.5. X2 is 1.8333, and x3 is 7.6667. Okay, so once everything is on a single page, it's kind of easier to write. So now we'll solve for x1 iteration 2 using this formula. So 7 minus x2, 1.8333, minus x3, 7.6667, divided by 2. That's negative 1.25. So I'll update the values, 1.25. X2 is 1.8333. X3 is 7.6667. Okay, now new guess, x2, iteration 2, using this formula is 2 plus x1, so that's the new x1, which is negative 1.25, plus x3, so it's plus 7.6667, the whole thing divided by 3. .8056. Insert it here. X3 equals 7.6667. Okay, x3 iteration 2. Let's go by this formula. Minus 3 plus twice x1. Twice x1 is negative 1.25 plus 2 times x2. x2 is 2.8056. This comes out to be 0.111. So my new x1 is same as it was. x2 is same as it was. But then there's a new x3. Okay, so this one I would like you to complete. I'll give you the answer, but I would like you to complete yourself. So we want to compute x3, x1 iteration 3, x2 iteration 3, x3 iteration 3. Do the calculation yourself. I'll give you the answer I get. I get 2.0416, 1.3842, and 3.8516. So the solutions after this iteration are, well, these answers, right? Yeah, sure. You try it right away? Why don't you try? You have, I'll put it on the board. Try to see if you can get these three answers. See if you can do it in, it should take not more than 5 minutes to do it. So iteration, give me the solution x1, x2, x3. So 1, 2, 3. This is what I got, 3.5, negative 1.25, 2.0416, 1.8333, 2.8056, 1.3842, 7.6667, 0.1111, 3.8516. Okay, so I had shown you the computer-generated solution for Jacobi iteration method that was going for 583 iterations. This one actually converges in just 12 iterations, 17 iterations, sorry, as you can see. So it gives you the solution for, of course, 17 iterations, and this is perhaps one way to check. Of course, you can't do it in the exam, but you can check it at home. Okay, and you can check that the first 3 iterations we had close to the answer shown here.
Is there any reason why we wouldn't use this, like when we have the other one? You know, in between the two.
Oh, why would we use this? Yeah, so that's a good question. Why would you use that one which takes more iterations? I think it depends on the problem, and it's like you have a tool, and you want to use that tool on a problem, and one tool works well, but then the other tool for a different problem, different scenario, the other tool might work. So that's the reason why there are multiple methods. This probably works much better than the first one. Yeah. So yeah, you have a choice clearly in real world. When you have a problem, you choose. I'm going to show you one which is even better than this. So next one is this is the last one, and then we are done with this chapter. It's actually it's sort of mixture of the first two methods. So it's called a relaxation method. Okay. Here, this method can improve the rate of conversions of Gauss-Seidel method. So for this problem, we'll see that it converges faster than 17 iterations. Okay, so here what is done is, remember the difference between Jacobi and Gauss-Seidel is only in the way that update is done. You use the new estimate to make the update. Here, there's another modification to the update. And this update basically makes it faster. So for any iteration, a new iteration, I plus 1, if you use the previous iteration, that would be your Jacobi method. What Gauss-Seidel does is it uses the new, so it will not have this, but it'll have the new xi plus 1 as it is computed. So what this relaxation method does, it sort of combines the two. It takes a weighted average of the two. This is the Gauss-Seidel update. So it doesn't rely totally on the Gauss-Seidel update, but it also uses the value of the previous iteration. Okay, the unknown there is omega, but that omega is a user-chosen constant. Omega is typically between 0 and 2. If you choose omega between 0 and 1, this method is known as successive under relaxation. SUR. If you use the update between the omega between 1 and 2, it's called successive over relaxation. SOR. Okay, so clearly you can do the same thing we did, and I don't want to repeat this. So what I'll do is I'll put down the problem which we solved, like the same problem, and then I'll give you the table as generated by my computer code, and we'll not really solve this by hand. Okay, so the only change here is that I need to tell you this, and I need to tell you that use relaxation method. And then this is the new thing. And as I said, I will not do this by hand, but you should be able to do this by hand. I'll make you do it in the homework. So this is the table generated by my code, and I'll be sharing code in just a bit. Okay, so you can see that this one converges in just 12 iterations, much faster than Gauss-Seidel or Jacobi. Now, it's very specific to the tuning parameter omega. If you use a different omega. I just basically tried a bunch of omegas and saw what gives me a fast solution. But if you use a very different omega, you may actually end up taking more steps than Gauss-Seidel. So all these methods, at least the iterative methods, are very subjective in the sense they depend on the problem, and then they depend on in this case, the constant chosen.